Let's look up. We'll be looking at stereoisomerism in monosaccharides. Now, we've seen what monosaccharides are. First, before we look at the stereoisomerism in monosaccharides, let's know what stereoisomerism is, or what stereoisomers are. Stereo means orientation in space. Orientation in space. We already know that isomers are compounds having the same what? Molecular what? Formula, but what? Different structural formula, right? Now, stereoisomers, they have the same molecular formula. They have the same structural formula, but different orientation of the atoms in space. So, stereoisomers, everything remains the same, but the orientation of the atom in space, that is what differs. So, we are going to look at stereoisomerism in monosaccharides. Let me give an example. If you have something like this, now, if you look at these two molecules, you agree with me that the molecular formula will remain the same, right? Is it not? How many carbon do we have here? How many hydrogen do we have? 3, 4, 5, 6. 6, right? How many oxygen do we have? And same thing here, right? So the molecular formula remains the same. If you look at the structural formula is still the same. But the orientation in space. Now if you check, OH here on the second carbon, is it on the left or right? The OH here is on the, that's the only difference here. So these two things, they are stereoisomers. Now, to identify stereoisomers, we have to know the idea of chiral or asymmetric carbon, because that is what we use to designate stereoisomers. Chiral or asymmetric carbon. Now, a chiral carbon or asymmetric carbon is any carbon that have 4 different substituents, 4 different atoms attached to that carbon. Take for example, if you look at this carbon here, carbon is tetravalent, right? It's supposed to have 4 bonds, right? Is this carbon chiral? Let's look at the 4 substituents attached to it. Hydrogen is one, right? The whole of this is attached to this, right? But yeah, this is like 2 oxygen, is it not? We're having a double bond. Anytime you see a double bond attached to carbon, just know that compound, that particular carbon is not chiral. If you look at this carbon, is this carbon chiral? Yes. Let's look at the 4 substituents. Hydrogen, this one, and this one. And you notice that all the substituents, all the attachments on this carbon are different, right? So since all the carbon, all the substances or substituents attached to this carbon are different, we say this carbon is what? Chiral. If you look at this other carbon, is this other carbon chiral? This other carbon can be written as this. I did not change anything, right? If you look at it, all this one attached to this, OH, hydrogen, hydrogen. You can see 2 the same substance, right? Same substance attached it. So this carbon is not chiral because these 2 things are repeated. So for us to have a chiral carbon or asymmetric carbon, all the substituents on that carbon must be what? Different. So yeah, how many chiral carbon do we have? 1, right? Good. Here the same thing, we have only 1 chiral carbon. Now, if you've identified the chiral carbon on that compound, to know the number of stereoisomers that compound will have, all you have to do is to use this formula. The number of stereoisomers is equal to 2 raised to power what? N. Where N represents the number of what? Chiral carbons. N represents the number of chiral carbons. Meaning if we are looking at this compound on the board, this is glyceraldehyde. This is glyceraldehyde. If you are looking at glyceraldehyde, the number of stereoisomer glyceraldehyde we have is what? 2 raised to the power what? Because the number of chiral carbon here is 1. The number of chiral carbon is 1. Then the number of stereoisomer will be 2 raised to the power 1, which is what? These are the only 2 isomers we can have, stereoisomers we can have. This one that the OH is on the right, and this one that the OH is on the left. If you notice, you will see that, you see the adjustment is just on the chiral carbon. One is on the left, and one is on the right. Now, any compound, listen to this one attentively. Any compound you see, the OH on the chiral carbon is on your right. The OH on the chiral carbon is on your right. You designate that compound with D, meaning dextrorotatory. Any compound you see with the OH on the chiral carbon on your left, you designate that one what? L. So this is D what? Glyceraldehyde. And this is what? L what? Glyceraldehyde. So if the OH on the reference carbon is always the penultimate carbon, that is the carbon adjacent to the last carbon. So if you are counting from down up, the second to the last carbon is what we are always using as a reference to designate D or L. So if you want to know if a compound is D or L, just check the OH on the second to the last carbon. If it is on your left, you call it what? L. If it is on your right, you call it what? D. Any question? I'll give you something to do for me now. We all know the structure of dihydroxyacetone, right? Let me give you the structure. Now, in your notes, identify the chiral carbon present and state the number of stereoisomers this compound can have. So do that for me. If you are done, call my attention. This is dihydroxyacetone. Identify the number of chiral carbon and state the number of stereoisomers this compound can have. If you are done, call my attention. So if you observe in this compound very well, you will notice that how many chiral carbon do we have? There is no chiral carbon, right? This is not a chiral carbon. We have 2 hydrogen. This is not a chiral carbon. It has double bond. This is not a chiral carbon. So how many stereoisomers can we have here? Only one, right? Because number of stereoisomers is giving us 2 raised to the power what? N, right? So 2 raised to the power n. N represents the number of chiral carbon. Is it not? So the number of chiral carbon here is what? 0, right? So 2 raised to the power 0 is what? So this is the only one we can have. This is the only one we can have. Alright, so that's that. I'm going to take another example. If you look at this structure here, please look up. Now please look up because I want to say something very important here. Look up. If you look at this compound on the board, is this a monosaccharide or a disaccharide? Monosaccharide, right? Is this a triose, tetrose, pentose, hexose, or what? Hexose, right? Because it's having how many carbons? Is this an aldose or a ketose? add those because we have aldehyde functional group, right? Now, is this, okay, this is the structure of glucose. But first, is this D-glucose or L-glucose? D-glucose or what? D-glucose or L-glucose? Now, to identify if it is D or L, all you have to do is to look for the reference carbon. And the reference carbon is always the penultimate carbon. That is the second to the last carbon. Are you seeing it? That is the cheat. Just look at the second to the last carbon. Now, the OH on this second to the last carbon, is it left or right? Right, right? So, since it is right, is it D or L? So, this is D-glucose. Do you understand? Just look at the OH on the penultimate carbon. If it is right, dextrorotatory. If it is left, levorotatory, L. Now, if I have something like this, if I have something like this, you notice that the only thing I did here, please look up. This is just like a mirror image of this one, right? Because I flipped it this way. If you look at position 2 here, the OH was right, is now left. This one was left, is now right. Right is now left, right, left. Do you get? So it's just like I flipped it. Now, this one, will you say is L-glucose or D-glucose? L-glucose, why? Because the OH on the penultimate carbon is on your left, right? So this is L-glucose. Please notice that I did not just change only this penultimate carbon. I flipped everything. It's like a mirror image. Now, how many stereoisomers can we get from this? To get the number of stereoisomers, you identify the number of what? Chiral carbon, right? How many chiral carbon do we have here? Is this a chiral carbon? No, right? Because we have a double bond. Is this a chiral carbon? Yes, right? Because we have 4 different substituents. This is one, this is one, this is one, and the whole of this is another one. Please, not only this carbon, the whole of this. Now, this, are they different? They are all different, right? So this is a chiral carbon. Is this also a chiral carbon? This, the whole of this, and the whole of this. So this is also a chiral carbon. Is this a chiral carbon? Look at this one very well now. Is this a chiral carbon? It's a chiral carbon, right? 1, 2, 3, 4. They are different. Chiral carbon. Is this a chiral carbon? 1, 2, 3, 4. This is a chiral carbon. Is this a chiral carbon? We have 2 hydrogens, so this cannot be a chiral carbon. Remember, for it to be a chiral carbon, we said something. We must have 4 different substituents. So how many chiral carbons do we have here? And therefore, the number of stereoisomers will be what? The formula is what? 2 raised to power what? N, where N represents the number of what? Chiral carbon, right? So 2 raised to power N is what here? So this will be what? So you notice that glucose, we have a total of 16 stereoisomers. We'll just be changing the position of the OH. We'll be changing the position of the OH. So that's that. That's that. Let me say something. For you to designate something as a chiral carbon, there are 2 criteria. For you to designate something, please listen attentively. For you to designate carbon as a chiral carbon, there are 2 things you must look at. Number 1 is they must have what? 4 different what? 4 different substituents. That carbon must have 4 different substituents. And number 2, the carbon must be optically active. I said for you to designate something as a carbon, as chiral carbon, one, it must have what? 4 different substituents, and it must be what? Optically active, meaning it should rotate when exposed to plain polarized light. It should rotate. But you cannot look at this compound and say the way this compound is, it can rotate too. So if you want to assign here, all you have to do is you look the one that have 4 different substituents. But the 2 rules in assigning chiral carbon is 4 different substituents and rotating plain polarized light. That is optically active. Is that understood?